The objective of this video is to learn different types of reactions in aqueous solution and to practice writing equations for these reactions. By now you know how to write and balance certain chemical equations, and in addition to balancing chemical equations, it is important to pay attention to the phase notation, which shows the physical state or the phase of matter. You already know the three different states of matter: solid, liquid and gas. We usually show these symbols, this phase notation, as a subscript in a bracket. And then AQ mean aqueous solutions. If a substance is dissolved in water, we use this notation. So if you find this AQ notation with any of the substances in the equation, that means your substance is dissolved in water. For example, if you take this given equation for calcium carbonate, you will see that calcium carbonate is in solid form. Why? You have the phase notation S given as a subscript. And then calcium oxide, the product, one of the product is in solid form and the other product is in gas form. So this phase notation is important in reactions. It helps us to categorize certain reactions based on whether it is going to be a precipitation reaction or is it going to be a gas evolving reaction. So there are many different ways we can classify reactions. You have already learned one way we classify. Another way is based on the different types of products we get. So that is why these symbols are going to be important in order to figure out what is going on in terms of physical state of matter. Right. One type of reaction you are going to learn is precipitation reaction. So in these precipitation reactions, we usually start with clear solutions. You can see in this given equation, you have lead nitrate, and you have learned the solubility rules. You know by now that nitrate is completely water soluble. So that means it completely dissolves and dissociates. So you will have a clear solution. And then sodium iodide. Sodium is a group 1 metal. Anything from group 1, they completely dissolve in water. So you can see a clear solution. And then when you mix these two, now you know the type of chemical reactions. Examine what's happening. Initially sodium is sitting with iodine. On the product side, now sodium is sitting with nitrate, which is the partner of the other ionic compounds. So you can see that there is a double displacement. The partners, the cations and anions, have exchanged their partners. So these precipitation reactions are usually double displacement reactions, and you will find when you mix two aqueous solutions, water-soluble substance, you mix them together, you get a solid. So by paying attention to this notation, you can find which substance has been solidified. And then the other product, it is in the aqueous form, meaning it is again dissolved in water. Dissolved, and because it is an ionic compound that dissolves, it dissociates as well. So this yellow substance you see here is actually lead iodide, which is a solid. So that means if you try to filter out, you can actually filter out this yellow lead iodide. So precipitation reactions, in general, they're displacement reactions, and you will find an insoluble product on the product side. Now the precipitation reactions can be shown in three different ways. One way of showing this precipitation reaction is the molecular equation. Why do we call this as a molecular equation? examine this whole equation. Do you see any charges? Do you see any ions? No, you don't see anything. But what you see here is that the formula and the notation indicating the phase, that's all. So in an equation, if you have everything as molecules, charge neutral, we call that as a molecular equation. The second way we can represent this precipitation reaction is by complete ionic equation. In the complete ionic equation, what we show is all ions, meaning for any substance that dissolves, we have to dissociate and show the ions. So how do you know it? Use your knowledge of solubility rules and also the symbols that's given. If you have anything, any molecular substance given with aqueous state, that means this is going to dissolve and dissociate. How do you know it's going to dissolve and dissociate? Because you know this is an ionic compound. How do you know this is an ionic compound? You have a metal and a nonmetal part. Every time you have a metal and a nonmetal part, you have an ionic compound. And if that ionic compound comes with this AQ sign, it means it dissolves. If it dissolves, it dissociates into cation and anion. So that means for every molecule or every substance that come with every ionic substance that come with AQ subscript, you can separate it into the two ions. And note what else we have done. We have balanced the equation. We have properly balanced the molecular equation. So it is the balanced equation. Now we are separating into separate ions. So every species that comes with AQ sign, again, you can see KCl and you can see the stoichiometric coefficient, this coefficient 2. That means you have two KCl molecules. So if you break down this molecule, you should get 2 potassiums and 2 chlorines. What this 2 KCl mean? You have 2 molecules, 2 of them. And when this breaks down, you get K plus from that and Cl minus from that. This gives K plus, this will give Cl minus. So these K pluses is what shown as 2K plus, and this 2Cl minus is these 2 Cl minuses. And then next substance we have lead chloride. You see it's in solid form. So solid means it is not dissolving. Since it does not dissolve, we keep it exactly like that. We cannot break it down into ion. Why? It does not dissolve. So what is shown in complete ionic equation? Everything that dissolves. And then you have potassium nitrate. You know potassium nitrate is going to dissolve. Again, you have 2 of them, so you have 2 potassium pluses and 2 nitrates. The other way we can represent these precipitation reactions is by the net ionic equation. How do we get the net ionic equation? By removing the spectator ions. So what is the spectator ion? The spectator ions are the ions that do not participate in the reaction actively. What does that mean? If you can find the ion sitting on reactant side and product side as an ion, that means it is not doing an active reaction. It's just sitting there in the solution, watching what's happening. So that is why we call it as a spectator ion. examine this equation. Who is present in both sides as an ion? You can see nitrate. Nitrate is sitting on reactant side, and you can find nitrate sitting just like that on the product side. What else? How about potassium? You have potassium on reactant side and then potassium on the product side. So in this particular reaction, you can see nitrates and potassium, they are not doing a real reaction. They are on both sides just sitting there watching. How about lead and chlorine? Now on the reactant side, you can find lead in the ion form, chloride as an ion form. But on the product side, they are no longer ions. They have made a solid. So they have done an actual reaction where you can notice that aqueous state resulted in a solid substance, while the other two are staying as spectators. So these two are going to be your spectator ions. So the net ionic equation shows you the active reactions. Show the active reaction. So what is your active reaction? Lead ion combining with chloride ion to give lead chloride. So this is going to be your net ionic equation. So in order to predict these things, if just in case, assume this subscript, the phase, is not given. So in that case, you need to know the solubility rules to predict these three different type of equations. Alright, let's do some examples. You're given in the first problem, you're given the molecular equation. When you examine the equation, you can see that it is given and it's already balanced for you. So what you have to do here is write the complete ionic equation and net ionic equation and identify the spectator ion. So I'm going to pause the video. You also pause the video and try to write it down on your own. Alright, now in this equation, it's already written and balanced for you, and it shows you the physical state or the phases of materials. So that means if you have the ionic compound as AQ, that means it can completely dissolve and dissociate. So if you have two potassium chloride molecules, you get two potassium ions, and make sure all the ions are dissolved. They are all surrounded by water molecules. So you have to show this AQ in brackets for all ionic species. You have two chlorides, then you have lead, and this is the subscript you see, so you know lead is 2 plus. You have nitrate, and you know there are two of them. You have potassium nitrate, you have two potassium and two nitrates. You have lead chloride, and see what you have is a solid form, so it does not separate, it stays as lead chloride solid. Now examine both sides. Who stays as ionic form on both sides? That is going to be potassium and nitrate. On both sides, it stays there like that. So your spectator ions are potassium and nitrate. So your net ionic equation is going to be lead ion, so these two are the spectator ions, and chloride ion. Gives you lead chloride solid. Now in the next equation, you have zinc chloride and lithium nitrate. Now this is going to be a precipitation reaction. You can do the double displacement and see if there is anything actively going on. So do the double displacement. Pair up zinc with nitrate and then lithium with chlorine. Lithium goes with chlorine. And then it is very important that you actually balance the equation. See if this equation is balanced. It is not, because you have two chlorines here. You have to have two on this side. Now you have two lithiums, so put 2 as the coefficient. Now the nitrate, now the equation is balanced. Now I have not given the physical state or the phase of this material. What are the physical phases for this? Lithium chloride. Lithium is group 1. So is it soluble in water or not? Lithium chloride is going to be water soluble because lithium is in group 1. So you can put AQ for that. And then zinc nitrate. How about this one? Is it water soluble or not? We have nitrate. So that means this is also water soluble. So is this a precipitation reaction? No, this is not a precipitation reaction. You have a double displacement, but there is no precipitate. Why? When you use the solubility rule, you can predict that all the products you get, they dissolve and dissociate in water. So there is no precipitation reaction, no precipitate. So what does that mean? That means all ions are spectator ions. So what are the spectator ions? All of them. Even think about zinc chloride. You are given aqueous sign. So that means zinc is in dissolved form. You have chloride, lithium, and nitrate. All of them are spectator ions and there is no net reaction. Another exercise. Now here you are given the words. Now this can be a little bit more complex than the previous example. Why? Because you are given the names and you are supposed to write the formula for the given reactants and then write the chemical equation. By now you know how to write the formula by reading the name. So pause this video and take a moment to write the formula and write the chemical equation. Alright, so I will do the first one, sodium carbonate. Sodium, the symbol is sodium, and when you go to periodic table, it's in group 1. So that means it makes the +1 charge. And the carbonate, that is a polyatomic anion, CO3, that is the charge. If you are not familiar with writing the formulas still, this is how we do it to achieve the charge neutrality. So your formula is going to be sodium carbonate. Now you have got that. Now think about the solubility of sodium carbonate. Is it water soluble or not? It is soluble. Why? Sodium is group 1. Everything in group 1 are water soluble. Second one is iron chloride. This says iron 2. So that means you have Fe 2 plus and chloride, that is from group 7 halide, it makes -1. Find the charge neutrality. Formula is FeCl2. Is this water soluble or not? It is. Why? All chlorides are generally water soluble except for lead and silver. And you know the precipitation reaction, they go through double displacement. Exchange the partners. Now pair up sodium with chlorine and iron with carbonate. If you want to pair up sodium with chlorine, you know sodium is +1 and chlorine is -1 from here. So what you get is sodium chloride, and you know it's soluble in water. Pairing up iron with carbonate, do the same thing, you will get iron carbonate. Now carbonate, you know from solubility rules, it is usually not water soluble. So it is going to be in solid form. See if your equation is balanced. Is it balanced? Not yet. You have 2 sodiums over here. So put the coefficient 2. Now you have 2 sodiums and you have 2 chlorines. Now the equation is balanced. Write the complete ionic equation. Everything with AQ you can separate into ions. So you can write it as you have 2 sodium atoms. So you can write it like this. But you don't do the same thing for carbonate. Why? This carbonate act as a discrete unit. It's a polyatomic ion. This part. Plus iron carbonate is in the solid form. So I'm going to leave it as a solid. And you can find what your spectator ions are. Your spectator ions are going to be sodium and chloride. So these two are not participating in the reaction. Your net ionic equation is iron Fe2 plus and carbonate, giving you iron carbonate. Right. Go ahead and try the second one as well. Alright, so if you're trying to write the formula for ammonium phosphate and zinc nitrate, ammonium is a polyatomic cation with a +1 charge and phosphate is 3- charge, and this is how you figure out the formula for ammonium phosphate with the charge neutrality. And then for zinc nitrate, zinc makes 2+ ion and nitrate 1- charge, and with the charge neutrality you get zinc nitrate like this. And then these are precipitation reactions. So you can see a double displacement process taking place. So that means the partners are exchanging. Initially you have ammonium with phosphate, but when the reaction takes place, ammonium is exchanged with nitrate. So you will find ammonium with nitrate. You're going to find zinc with phosphate. And this is how you get zinc phosphate formula. Zinc has 2 plus charge. Remember zinc, where can you find zinc? You will have to check the D block. And then phosphate 3 minus charge to the exchange. You will get the charge neutrality and the zinc phosphate formula like I have shown here. So once you have the chemical equation, now this is the molecular equation why you don't see any ionic species. Once you get the equation written, balance it. Now I'm going to balance this equation and I'm going to examine things in both sides. Remember, when you have polyatomic ions, consider the polyatomic ion as a discrete unit instead of trying to breaking them down into each and every element. Now in this end, I can see 2 phosphates with the subscript. So I have 2 phosphates, but on this end, I have only 1 phosphate. So I'm going to put the coefficient 2. That gives me 2 phosphates, but now I'm going to end up with 2 into 3, 6 ammoniums. I need 6 ammoniums, so I'm going to put the coefficient 6 for ammonium. Now I got 6 ammonium, that result in me 6 nitrates. I have a 6 nitrate on the product side, so I should have 6 nitrates on the reactant side as well. But what I have is only 2 nitrate, so I'm going to put the coefficient 3. 3 into 2, I get 6 nitrate, and at the same time I'm getting 3 zinc atoms, and that perfectly balances with these 3 zinc atoms. Now my equation is properly written and balanced. Now I'm going to write the net ionic equation, the complete ionic equation and the net ionic equation. So everything written here, and also you have to figure out the phase of the written substance. This is ammonium nitrate. Ammonium and nitrate, they are always soluble, so this comes as aqueous and zinc phosphate. Recall solubility guidelines. Phosphates are usually not soluble. So this is going to end up with a solid state. So everything with aqueous, break them down into ions. Alright. The complete ionic equation, consider the total number of ions as well. When you break down dissociating ammonium phosphate, consider how many ammonium ions that will be released. 2 into 3, you end up with 6 ammonium ions. However, you end up only with 2 phosphates. Why? You can see that 2 into 3, you have 6 negatives here. That perfectly balances with the 6 positives over here. And again, you have 3 zinc atoms and 2 into 3, that is 6 nitrates. You have 6 ammonium ions, which perfectly balances with the reactants and the 6 nitrate ions. And your solid form exists as zinc phosphate. You can see what your spectator ions are. These two are going to be your spectator ions, ammonium and nitrate. Your net ionic equation is going to be zinc plus phosphate. You get zinc phosphate. That is how you do these problems. So you have to continually practice what you already have learned, naming compounds, writing formula, because you can see they are all connected to each other. If you try to forget one thing, you will have hard time figuring out these parts.